Okay, so let's start with the background for data preprocessing and feature extraction. But if you see the link, so I assume that you can access this link from the. Sorry. So Rafi, why is that? Yeah, so what I'm saying here, so I hope you can access this website. So from the Google Doc or from the box, you can download all the materials. So the first material today, we're going to talk about background for data processing and feature extraction. And there you will find two set of slides. First set of slide is associated with the feature extraction. And then the second part of the slide, the first part of the slide will talk about generic text processing, and then second part of the slide will talk about how to extract the features from the text documents and the malware executables and those type of things. And then there will be a lab on that, so we'll talk about that later. So if you have any question, please feel free to interrupt me at any time. Do not wait for the last minute. So you can ask me any question at any time. Okay, so first I'm going to talk about the text classification. So there are, I think for this workshop, we came up with the 6 modules. So the first module will be very basic stuff, you may already know it. So there we'll talk about some text classification. So for that, the goal here, once I introduce those concepts, the idea here is I will try to tell you the motivation behind this text processing, and when I will try to introduce you what are the challenges we face when we process the text data, and then what are the text mining tasks we want to do it, and then we will in this workshop, the idea is you have to do a lot of hands-on. So for the first hands-on will be we have to crawl some Guardian websites where we will crawl the we will crawl a bunch of news articles. So for that, I will introduce you briefly the web crawling, how to collect the data, and then also we will do some malware classification, whether a executable is malware or benign. So for that, I will introduce you the malware data little bit, how to extract the features from malware data. So that's the goal here. So the motivation behind this work is nowadays you will see a lot of text data are around, text documents we will face. So for example, a lot of computer malware threat reports are generated every year. Threat reports are usually unstructured text format, and it requires human to interpret or classify it and so on. So when human will involve in the loop, what will be the problem? Problem is usually human is expensive and you have to buy human time. You have to spend money. And on the other hand, humans sometimes come up with a subjective judgment and so on. So, and then motivation for why you need to process the text data. So the reason is this. Nowadays we have lots of data, but most of the data fall into this unstructured text. So 80% to 90% of the world's data will be associated with unstructured format. So web pages, emails, technical documents, books, text messages, movie reviews, those are examples of the unstructured text. So goal here, given this unstructured text or document, our goal here is to extract the information or classify them. So for example, we crawl some news articles and we want to identify the news article, whether it's a sports news or financial news or entertainment news. So this problem you can identify it as a classification problem. So we crawl a news articles and then we want to label it, whether it's a sports news, whether it's a financial news, something like this. So that will be known as a classification problem. On the other hand, let's say in the news article it was mentioned that certain event happens in, say, in Afghanistan, and then it was reported from, say, Paris. So in that case, our goal is to identify what are the source and target are involved in that news. So when a political crisis happens at a certain location, so it will be mentioned that the source is this and the target is this, and the certain actions are happening. Let's say verbal conflict or material conflict is going on. So our goal is to identify those type of metadata. So it's not trivial to identify those type of metadata, and Dr. Patrick Brandt, he will present those stuff more details on Wednesday, how to extract those metadata. Okay, so now when I talk about the data, keep in mind that data can be categorized or identified into 3 distinct groups. One is called structured text, the other extreme is called unstructured text, and the middle we have what we call it semi-structured data or semi-structured text. So now in this case, when you talk about the typical relational database, like all this Microsoft, say IBM DB2 product or Oracle, those product uses the relational database. Nowadays they use object relational and database and so on, but that mostly deals with the structured data. So there the information will be stored in database, and it follows, each of the records will follow a certain fixed number of attributes, what they call it schema. So now this is good for if you have a data like this, and we can process it using the database and so on. On the other hand, other extreme is the data do not follow any strict guideline or any fixed set of schema or attributes. So you have a bunch of documents, and each document has its own, you cannot describe each document, all documents cannot be described by a common set of attributes. That is not feasible in unstructured data case. So it doesn't have any predefined structure. So for example, a simple text document, PDF files, photos, malwares can fall into this group, unstructured data. And in the middle, we have a semi-structured data, which is, so one extreme you have a structure or some sort of schema to description of the data, and other extreme is unstructured data, which we don't have any predefined structure or schema. So that's unstructured. And in the middle, we have a semi-structured data like HTML, hypertext markup language document, HTML page, or XML document fall into this category, semi-structured data. Now, semi-structured data, what happened? In HTML case, you have a predefined set of tags and their values you can come up with. On the other hand, XML case, you can come up with your own all these tags and the values and so on. So what happens? Okay, so is it clear? The point I'm trying to make, data can be categorized into one of the 3. When you have a data that you can classify or categorize it in one of the 3 groups: unstructured, semi-structured, and structured. And many cases we deal with the structured data, and in this workshop we'll focus on mostly on the unstructured data. So here just give you some introduction about structured data. So this is a one student table in a university database. So each record will represent the student's name, the date of birth, and the major. So you can see here we have how many records we have. Total 5 records, and each record will be described by a fixed set of attributes. That I call it, we have a predefined structure for each of these records. So that's called structured data, and structured data is easy to process by using SQL, structured query language, and so on. Again, please feel free to ask me a question at any time. So here, second one is semi-structured data. Here we have a HTML page, and that page has a bunch of links and the tags and the values. So it has a predefined, so is in the semi-structured data it falls into. On the other hand, unstructured data, like this is a simple news articles that talks about Brexit. So there we have this document is just talks about certain things, but it consists of a number of bag of words. So in that case, this document does not follow any fixed structure and so on. So we cannot represent them using structured data or relational database. So what you learned so far for the structured and versus unstructured, these are the things we learned. So characteristics for the structured data, we have a predefined data model and easy to search using SQL, for example. On the other hand, unstructured data, there is no predefined data model we can use. And the image, video, audio, then those can fall into these categories. Then in terms of the storage for the structured data, we use the relational database. Basically, it will be stored in a table and stored in a file. And data warehouse solution or relational database solution, we can use it. And for unstructured data, nowadays in a big data area, they call it NoSQL system. Not only SQL system can be used, those type of things. And then for indexing purpose, you can use inverted index like Google uses inverted index. So, and then typical application can be the reservation system, library system for the structured data inventory control. Airline reservation system can use the structure. Basically, the relational database they use, and their data will be structured. On the other hand, when you have a word processing system you want to use, that can deals with unstructured data and so on. Okay, so again, unstructured data formats is that email messages, word processing documents, web pages, and business documents. So these are the. So in this workshop, at the beginning, we'll focus on the text document or textual document. So the idea here, textual document, we're talking about all this email content or the word documents and so on. So that can fall into this. On the other hand, the textual document belongs to the unstructured data, and at the same time, there are other non-textual data we can have, like video, audio, images, and so on. So in this lesson, first we'll focus on the unstructured text, and so now here I try to motivate you that nowadays when you deal with the data, most of the data falls into unstructured data format. Like 70 to 80% of the data represents unstructured data in an organization. So, and this rate is growing in exponential. So if you see the timeline, x-axis represents the timeline year, and y-axis represents the all global data in zettabyte. So you can see the curve is exponential in nature. Okay, now I want to introduce you a little bit more about text analytics and its application. So what is the purpose of the text mining or text analytics? The purpose of the text mining is to derive or extract meaningful or useful information that can be used for decision making and so on. And here the focus is unstructured text. From the unstructured text, we want to extract some useful information or some sort of unknown patterns and so on. So for example, I said incoming text document, I want to label it whether it's a sports news or financial news. That will be a classification problem, text classification. On the other hand, given a text, we want to identify, let's say the text talks about some political crisis, and political crisis involved between, say, Iran versus, say, UK. Recently there is a problem. So the source will be Iran and the target will be UK, and the crisis in some verbal conflict is going on. So that type of thing we want to extract. So that's part of the text mining. So what type of information we are looking for? We are dealing with a huge amount of data, so, and we want to derive high valued information from there. And text mining possible applications you will hear, like spam filtering. So when you get your email messages, you will see that there is a automated system that identifies incoming email is a spam or non-spam. If it is a spam, then it will go to the spam folder. If it is a non-spam, it will go to the some sort of other folder. So there we can use the text classification. So similarly, foldering purpose, let's say you have you maintain multiple folders. Some folders are associated with the, say, your office work. Some things talks about, say here as an example, I should try to tell you that incoming text document, I want to categorize it in the complaints, deals, and applications. So these are the class levels we have. So when the message will come, or the system text analytics will automatically label it either one of these categories, and then once I identify the category, it will forward that to that, the system will forward that document to that folder. Okay, so what I try to say, I just give you a little bit hints what we are planning to do in the lab 1. So we will crawl bunch of news articles from the Guardian website. So it will talk about certain things. Each document will talk about certain things, and then using our machine learning technique, what we call it a classification technique, we will classify this incoming news into either one of these categories, say sports, business, education, science, something like this. So in this case, the assumption is each document will belong to one particular category. So, but in real life, it is possible that a document may belong to more than one categories. A particular document may be associated with the sports news. At the same time, it may be associated with the financial news. Say, for example, they're talking about, say, a famous basketball player, and then that player talks about some financial dealings. So in that case, it can be labeled as a two groups. One is the sports, the other one is the financial news. These are the things that are possible in classification case. And then, so recall that what I try to say here, we crawl news articles from the Guardian website, and once we crawl it, so then our goal is to categorize these incoming news articles into one of these categories. So that's our goal. And so what is the benefit of doing this type of classification? Can you tell me? Let's say you like sports news. So next time when you go to the Yahoo News, so from your profile, the system already knows that in the past you browsed through the sports news a lot. So now new news articles pop up that article is associated with the sports. Then the system would automatically recommend that article to you. So that we call it, it can be used for the personalization purpose. So this type of classification will help you to do the personalization later. So once you identify the right label for each of this document, then we can use it for later for personalization purpose and so on. Because keep in mind that when you crawl these articles we don't know what will be the label. So once we know the label, then we can do a lot of personalization and a lot of other things. So again, please feel free to ask me questions if you have a problem. Okay, so what is the problem when you do the text classification or text mining or text analytics? There are a bunch of challenges we will face. So first of all, the articles so this is a article, right? That article talks about, say, UK new Prime Minister will be Johnson, right?
Who's got it?
Oh, okay. That's fine. Okay. So let's say that here the article.
Please God, no, not Boris Johnson.
Okay. Now I'm saying that let's say that article talks about some of the. So this article, let's say, associated with the sports, but this article will consist of what? Consists of a set of words. So now computer cannot process those words, it can process only the numbers. So the idea here, this document will be presented as a vector. So the vector will be, so just think about the naive way you can represent this document, word document, as a vector like this. Word W1, word W2, let's say there are total 100 words. So the first word is president, let's say USA, something like this. So these are the W1 represents a president, W2 represents USA, something like this. So now if the president word is there, then in the vector representation this will be set to 1, let's say, for example. This is a very naive way you can represent the document as a vector. So then if the word W2 is present in the document, it will be represented as 1. If it is not present, then it will be represented as a 0. So that's called binary representation. So that way each document will be represented as a vector. Now let's say we have 1,000 documents, 1,000 documents, and all this 1,000 document contains total 10,000 distinct words. So this is my collection, 1,000 documents, and for this 1,000 documents I want to label it, and this 1,000 documents, all, if you take the union and find the distinct number of words, how many distinct words we have? Distinct. I don't know whether I hear it clearly, but how many distinct words we have? Let's say total 10,000 distinct words. So then the vector, each document will be represented as a vector, and the vector dimension will be total number of word will be, this will be 10,000, right? So now you can see that, so each document will be represented by a vector. Vector dimension will be W1, W2 all the way to 10,000. So 10,000 dimensions will have. So what is the problem? Okay, so this problem is called cuts of dimensionality of this type of text data. So text data, or when you talk about the image or the video even, that will face the cuts of dimensionality problem. The reason is each of the data point or each of the document will be represented as a vector, and the vector will have, in this case vector will have many dimensions, so 10,000 dimensions. Now how this dimension will cause a cuts of dimensionality problem? The problem will occur like this. Let's say if I give you a document and ask you, give me the document, you have in your database you have a 10,000, I'm sorry, you have a 1,000 text documents. So in our database we have total 1,000 text documents we have. And my query pattern, search query is this: give me a document, given this document, give me the document that are from this collection, which are very similar to this. That's my query. What is it called? Query by example, right? So this is my query document. I'm asking you, give me the document from this 1,000 documents, which is very similar to this query document. So what will be your approach? So the approach is, first you will convert this query document into a vector, right? So the vector representation, you will find what are the words are there, and then once you have those words, you will try to determine the word like this, W1, W2 all the way 10,000 dimensions. You will see W1 is appear in the document or not. If it appears, you will put 0, 1. If it appears, you will put 1. If it doesn't appear, it will put 0. W2 appears here, so it will be 1. W10,000 doesn't appear there, it will be 0, something like this. So this query document will be represented by vector like this. Now we already, from my text document live collection, I have 1,000 document, and each of these document will also be represented as a vector. So we have document number 1, document number 2, and then document number 1,000, right? And I'm just trying to motivate you how this thing works underneath. So I'm trying to tell you that query by example. So I have a 1,000 documents, and this is a one sample query document I have. I want to find the documents that are very similar to this. From this, I want to find the documents that are very similar to this query document. So what I will do, now I need to compare this query vector, document vector with this. I need to compare with this. I need to compare with this, right? So how do you compare it? So here we can do various ways to do the comparison using the Euclidean space. Just think about this document will be represented in a 10,000 dimensional space as a point. So if you consider a multi-dimensional space, this document will be represented by this vector, right? So in a multi-dimensional space, we will have a 10,000 dimensions. In this 10,000 dimensional space, this document will be represented as a vector, right? As a point. So now document 1, document 2, document, so if let us say document 3 is very similar to this query document, then what do you expect in a multi-dimensional space? This document 3 and the query document and the document 3 will be very close in a multi-dimensional space. Then if you calculate the Euclidean distance between these 2 points or between these 2 documents corresponding to 2 vectors, you will see the distance is very small. So that is the very basic idea. So now how the curse of dimensionality will come into play? So in that case, what will happen if I calculate the distance between document 3 comma let's say document I comma query document q doc q doc. So what I will do, I will calculate the distance like this, doc I, okay. So I will do what? So now doc I will be represented by W1, W2, W 10,000, right? So I will calculate the distance between W1 comma I, superscript represents the document ID. W1 Q square, W2 comma I, W2 Q square, W 10,000 I comma W 10,000. Okay, so the distance between these 2 documents will be calculated by Euclidean distance.
Is that the only?
No, this is the only, I just try to,
Okay.
there are other ways, this is not the best way. The better way for the document is cosine similarity. So that we'll talk about later. But here I just try to emphasize how the high dimensionality data will cause a problem. High dimensionality data will cause a problem that is known as a curse of dimensionality. That I try to explain. So now if I give you, just let's say if I give you 2 points, 10 comma 15 in a 2-dimensional space, and then another point is let's say 11 comma 13. So this is P and this is Q in a 2-dimensional space. Then if I ask you what will be the Euclidean distance between these 2 points, distance between P and Q, you will calculate something like this, right? 10 minus 11 square, 15 minus 13 square. Do you agree with that? So same idea we extended here. So this W, all this W, so W is the feature 1, feature 2. So superscript represents the document, either document I or the query document Q, and the subscript represents the features. So the first feature, second feature, that way you will calculate. So here we have two-dimensional space or 2 features only, but here we are talking about 10,000 dimensions. Now when you calculate the similarity between 2 documents, that means you have to go through this 10,000 times, you will do the subtraction, right? And then you will sum it up, then you will take the square root. So only for 2 documents. But if you now, you have to do this not only for 10,000 times for 2 documents times 1,000 documents, right? So you can see here the comparison is very expensive. So if you can reduce this dimension somehow, instead of 10,000, if you can reduce it 500 dimensions, then there will be a significant savings you can achieve. So that this problem is known for high dimensional data. This problem is called curse of dimensionality, and for curse of dimensionality there is a way you can do it using some feature selection you can apply. So that's one way. So just for your, this is nothing that much relevant what I told you, but the main idea is when you have a very text data or image data, we will face the high dimensionality issue, what we call it curse of dimensionality, and that is exactly happening like this, what you calculate the Euclidean distance, for example. And furthermore, in text case, it introduces other problem. The problem is the text, the word has many meanings. So for example, in English, the bank has a river bank, it can be, or it can be the bank or the financial bank. So the bank keyword can be used in a different context and so on. So if you try to, so that may introduce challenges when you try to do the text analytics. And finally, what are the tasks we can do in text analytics? The first task is called text classification. So it's the task of assigning a document to one or more classes. For example, I tried to tell you that before. So incoming text, we want to label it, what class label we should give it to. So for example, for this text, we are saying this text actually talks about the film. On the other hand, this text should be classified, this part of the sentences should be classified as a science, say for example. And this part of the text should be classified as a business. So these are the classification problem. You need to do it in this hands-on exercises today. And then text mining has been widely used in a sentiment analysis. Say for example, when the former President Obama introduced the healthcare, that time it was known as Obamacare. So many people like it, and some people dislike it also. So you will see in the Twitter, people start to send the Twitter messages. So our goal is to, if it is related to Obamacare, we want to label that tweets, whether it's convey positive sentiment, whether it conveys negative sentiment, something like this. So that will be known as a sentiment classification. Some cases you can also categorize it as a neutral. So the idea here is, first we will identify a bunch of tweets. You know that in the Twitter, people can post their messages for very short messages, right? 140 characters. So now our goal is to identify if it is related to Obamacare. We want to label it whether it is a convey positive sentiment, or whether it conveys negative sentiment, or it is a neutral, something like this. So here we can, it is nothing with the Obamacare, it talks about movie review. So some of this one means negative sentiment, this one means positive sentiment, and so on. So I don't want to read, you can read yourself, right? And then also text mining can be used automatic summarization. So given a text articles, our goal is to identify or summarize the text. So you know, in English I heard that every paragraph, the first sentence in the paragraph is the most important sentence, convey the most important concepts. So that type of information can be useful for the summarization purpose. Then we can also use the text mining can be used for the text classification. So for example, you know that what is the difference between classification and clustering? Classification is a supervised task. That means you need some ground truth to build a model or some label data. On the other hand, clustering is unsupervised task. You don't need any label data and so on. So the idea here is I give you a bunch of articles and we don't have the label. I ask you to build from this text document, build 100, let's say build 10 clusters. So we have total 1000 text documents, and our goal is to come up with the 10 clusters or 10 groups. So the idea here is similar documents will belong to one particular cluster. So intuitively you can think about, if the articles talk about sports, say some basketball, related to basketball, then they should belong to one particular group or clusters. So that will be known as a text clustering. And there again, we heavily use the similarity calculation and so on.
So when you're creating 10 classes, it's not necessary.
I'm sorry, 10 clusters, yeah.
So the point is not necessary that all 1,000 would go into those 10.
No. So in that case, if I have a 1000 document, so expectation is intuitively, if you assume that uniform distribution, so in that case cluster 1, cluster 2 all the way to cluster 10, you can assume that divided by, so I'm sorry, I have 1000, right? So it will be, you can assume that on average each cluster should have 100 documents, but in reality that may not be the case. Some cluster may have 200 documents, some cluster may have only 5 documents, that's possible. So I will, in this workshop I will introduce you how to do the clustering also when time comes, not today, probably on Wednesday. We'll talk about some of the clustering aspect in a different context for anomaly detection, but same idea can be applied for the text clustering also, because eventually the text document will be converted into a vector, and then after the vector it will be the same algorithm anyway. You can use clustering or anything. Then for question and answering session, text analytics can be used. Okay, so now I want to introduce you the web crawling, which will be used for your first hands-on. So motivation for the web crawling is to retrieve the web pages and add the representation to a local repository. A web crawler is a program or automated script that browses the World Wide Web in a methodical and automated manner. And the web crawler can be known as a other way like this. They sometimes will use those terms also. So the web crawler is a computer programs that roam the web. The goal of automating specific tasks related to the web. The role of crawler is to collect web content. And how does it work? It starts with a seed list, with a list of URLs to visit, which we call the seed. And as the crawler visits this URL, it identifies all the hyperlinks, hyperlinks in the page, and add them to the list of visited URLs called the crawl frontier. So from there, it will go to the next level. That way, the URLs from the frontier are recursively visited according to a set of policies. So what I meant is this. We'll give you the program, you just need to run it here and then crawl those pages. So we will give you a seed list, and then you will connect to the, in this case you will connect to the Guardian website or server, and then get the URL, and then when the page we fetch it, we will find what are the links are there. So from that link we will go to the next level, call the program again and find more pages. So to access the API, you need to get the API key. That's very important. So we are planning to give them API key. Am I correct? Okay. And then, so these are the search parameters we are going to use. So you need to provide your API key and number of, say you can mention the date and those type of things we can specify. And then here is a sample searching URL. So there we talk about, I think we are talking about a particular source date and the target date, and then 200 page maximum we can load, and then the API key we are providing here. And then the Guardian will respond to you with the JSON. The Guardian will basically return the result in terms of the JSON format. So this is the way it will give you the result. And then you will also get the content of the pages like this. So here, the important point is, once you crawl the page, you will see that the section name, that's the business in this case, that talks about the labels of this page. So this, basically the description of this is associated with the business. So the label of this article will be the business. So this will serve as your ground truth. This is the key important point, or key point I'm trying to make. And there is some headlines you can also use for your classification and so on. Okay, then next one. So we will talk about that more details when the time comes with the hands-on for that. Now I have to talk about a little bit malware data we're going to deal with. So malware is a malicious software, is any program or file that is harmful for the computer users. It includes computer viruses, worms, Trojan horses, and so And what the malware does, it steals the personal information, it deletes files, click fraud, it does a lot of bad things. You already know better than me. And then, so the growth of malware is exponential. So you can see here the various timeline. So now there's an arm race going on. A lot of new malwares are coming and so on. So the malware data we are trying to use, that will be taken from the Kaggle website in this hands-on. So that malware data set has a 0.5 terabyte uncompressed, and each malware has a ID, 24 character hash value, then a class level, what type of malware it is, an integer representing only 9 family names, which of the following may belong to. So these are the 9 types of malwares we are going to use. Our goal using machine learning, we want to, given a malware, we want to classify it one of this. And you can see the data distribution is not balanced. So these are the 9 types of malware. Yeah, so 9 types of malwares. And then you can see some of this malware has only 42 instances. So it's very imbalanced, not a balanced data set. So in that case, when you build a model, probably the model may not perform well. And then there is more description of the malware. Each of these malware types are provided here. And finally, one important point I try to make, I want to ask you, please pay attention, that although this is a hex dump, right, for the malware, but the data is organized a little bit weird way, in this case the Kaggle organized. So the first, how many? 2 byte, right? Yeah, 2 byte, right? Yeah, so first 2 byte or 16 byte represents some sort of address. So in the data set itself, it is there. And then this is the content of the hex dump. Then again you will see this data set, the byte, the address will be given to first 2 byte, and then again the content will be there. So here the address is, in this dump you will see the address plus the content. So you need to skip this part when you process the data. So far what I try to tell you, that data can be categorized into 3 groups in summary. One is unstructured, then one extreme, the other extreme is structured, and in the middle we have a semi-structured, and text falls into the unstructured data format. And in this case we focus on the text analytics. So I'll introduce you a little bit the web crawling, that you will learn more in the hands-on. Okay, so the next lesson I want to talk about text processing and feature extraction. So you want to take a, so okay, according to the, no, we have still time, okay, 30 minutes. So next we will talk about the text preprocessing and the feature extraction. So do you have any question for this material? So everything is clear? I think you already know those materials probably. So okay, so I tried to give you a hints before that how to generate the feature vector. So now I want to go to the more details about those feature vectors in the text. So that will prepare you for the hands-on number 1. Okay, so the goal here is I want to convey that how to do the text processing and how to extract the features, and then we will talk about more parts of the speech tagging, name entity, bag of n-gram representation, TF-IDF, and word embedding. How many of you know TF-IDF? So a lot of people. Okay, so these are the materials I already covered, and now let's talk about text processing. So there are some terminology where I'm going to use. So document means a coherent piece of text. The email message can be a document, and the corpus means a collection of documents. Text token means a block of text that has meaning. Word phrases can be an example of the text token, and vocabulary means the set of words represented in the corpus. So these are the terminology I'm going to use. So now this is the text document. Okay, so this is a text document. Let's say we crawl it from the Guardian news articles, and this text documents, you can see, basically consists of a bag of words, and each of this word in this case will represent a token, and number of words represent a phrase, contiguous words, and then these are my vocabularies here, and our goal is to do the classification, identify what will be the label for these articles. So we want to label it as a, for example, it should be labeled as a business. Do you agree with that example? I never check it, but I assume. So now I try to tell you that unstructured text such as tweet, web pages, or product reviews. So product reviews means when you watch some movies, sometimes you post the review, right? If you like the movie, you may say that the movie is great, please watch it. Or if so that's a product review, like movie review and so on. So use some pre-processing before it can be analyzed. So for example, so this is some sentence we get it from the certain website, and in this sentence, or you can see some of the words here, we don't have a stop word, but in English you will see that people use articles very frequently and so on. So those a and the are, sometimes they may not carry that much information, so they do not add to the semantic meaning of the text, so we need to remove those stop words. And then there is another in the text pre-processing. In the first steps for the text pre-processing, we have to remove the stop word. The second one, we are talking about the stemming, like connect, connecting, connected, all will map into the same root word, let's say connect. So in this case, we try to say introduction, introducing, introduces will map to the same root word. So that type of thing we need to do it in case of word stemming. And then from there, after pre-processing the text, so we will remove the stop word and apply the stemming. Then we will extract the features from the text document. So what type of features we are going to extract? The text feature extraction means the process of converting text from the textual representation to the numeric values. So we want to make it fixed length feature vectors suitable for machine learning algorithms. So that I try to tell you that. So the problem is the document 1, the document 1 may have say 500 total words. Document 2 may have 200 total words. Document 3 may have say 1000 total words. So you can see here, if you use those words as a feature vector, so in that case the feature vector dimension will be for document 1 will be 500, 200, for the document 2 it will be 200, for document 3 it will be 1000, something like this. So it's not a fixed length. So what do we do? In this case, we take all these 1000 documents and find out what are the distinct keywords we have, how many distinct keywords we have. I try to tell you that, let's say in this 1000 documents, the extreme example I gave, 10,000 distinct keywords we have. Then in that case, each text document will be represented by a vector having 10,000 dimensions. Very good. So that I try to tell you here. So machine learning algorithm cannot take variable length feature vectors. So that's why we have to come up with a fixed length feature vector. So that's why we take the union and come up with the 10,000 dimensions. Okay, so now here I will talk about a little bit more details about the feature extraction. So parts of speech tagging first. So parts of speech tagging is the process of assigning a parts of speech or lexical class marker to each word in a collection. Words that somehow behave alike, appear in similar contexts, perform similar function in sentences, undergo similar transformation. Say 9 traditional word classes of parts of speech we already know: noun, verb, adjective, and so on, right? So here I don't need to explain this, but here's some example for the noun, some example for the verb, and so on. Now we can also do more a little bit. So for that, what people use in an NLP area, natural language processing area, they use pen tree bank, that hand annotated corpus of a Wall Street Journal. They consider 1 million of words, and they try to identify 46 tags instead of 9 parts of speech. So those 46 tags are like this. So for example, let's say adjective will be, in this case, will be represented JJ tag. So noun will be represented NN tag, something like this. So these are the, instead of using 9 types of parts of speech, here we are using 46 tags. So here what I meant, say for example, if I have a sentence like this, so in that case 2 will be known as a CD and old will be JJ. What is the CD means? CD means in this case cardinal number. So that way we come up with the tag for a given sentence. For a word we want to extract the tag, or phrases. For a phrase we want to extract the tag. And then also name entity recognition system we are going to use here. That involves identification of the proper names in the text, classification into a set of predefined categories of interest. Here, given a sentence, our goal is to identify whether it represents a person, a particular phrase represents a person or location or organization. That type of information we want to extract. That will be associated with will be associated with the name entity. And for example, what I meant is this. So if I say the sentence is like this: John sold 5 companies in 2002. So in that case, John will be a person, and then 5 will be a quantity or numbers, and then the 2002 is a date. So something we need to extract. So we are going to use in this work, or in your hands-on, we are going to use Stanford Core NLP. So there it uses the name entity, NER will extract the persons, and it will extract the location information, it will extract the organization information. The 3 types of information we are going to extract. So given a text like this, the color represents each of these name entities we are looking for. So for example, location information, which one is location? Where is the location? I don't see the color for location. Is there any location here? No location? Okay, but so this is a person, these are all person, and then this is the organization, this is organization, this is organization, this is a date, and we don't have a location here. So our goal using Stanford Core NLP, we try to extract this name entities. And then the important part of the feature extraction, yeah.
So location is not necessarily identification period of time.
No, time is different from the location. So we will, the location, let's say this, that talks about,
It's the Welsh assembly, right?
which one?
This is the Welsh assembly, right?
Where is it? There is a location here?
No, I'm just working out the context.
Yeah. No, I'm trying to say that, let's say this talks about which country it represents. But let's say that this is related to, say, I don't know which country, MP, so probably it will go through the UK.
It's Wales.
Yeah, right, yeah, Wales, okay. Where is Wells? Mentioned in the text?
No, but the name and the fact that it was one already covered in 2010.
Oh, okay.
Because the S&P was in charge in Scotland and.
Sure. Yeah, so you're right. So let's say if there is a mention that this MP is from, say, somewhere in England, so in that case we need to identify that location. Or there is also a possibility that this incident took place at a certain area, but it was reported from a different location. So in that case, there are multiple locations might be there, right? So we will show you, Dr. Patrick Brand, he will show you on Wednesday that once multiple locations are mentioned, our goal is to identify the focus location plus where the actual incident took place, and then also if the reporting location, that will not be the focus location. So there is a way to deal with that. So we'll talk about that on Wednesday. Okay, so any other question? Okay, so now we are going to cover the important things, how to represent those documents as a vector. So the bag of word is a feature extraction technique. It's a text feature extraction technique which describes each document by a vector of the words occurrences count. There are two ways you can represent bag of words. One is a binary representation, or other one is called how many times it appears there and so on. But there is a problem with that approach. So before I try to show you this vector representation, word appears in this document or not. If it appears there, I will put 1. If it doesn't appear there, I will put 0, right? That's a binary representation of the bag of word. But there are other way you can also do it. If the word W1 appears 10 times in this document, then you will put, instead of 1, you will put 10. If it appears 0 times in this document, you will put 0. And W3 appears, let's say, 5 times in this document, you will put 5. So that's another way you can represent. Instead of binary representation, you will use frequency count. Now, this is not an effective model. And then another problem with this type of representation, what is it? The problem is, if you are looking for, let's say, when you Google it, you are looking for UT dollars. You are looking for a web page that contains keywords UT dollars, or that contains phrase UT dollars. So now there might be some pages that talks about UT, basically and then it talks about UT system, and then it talks about that UT system has many campuses, Austin, Dallas, then San Antonio, all of this. So in that case, when you look for UT dollars, what will happen? Probably this page will be returned to you. Although your intention is you are looking for a page where UT and dollars keywords appear together, next to each other, adjacent to each other, right? Now, the way we represent this type of vector representation when we use, it does not take into consideration the position of the word. Or that means bag of words ignores the location or position of the words in the document. So in the later phase, when you do when we want to look for certain phrases, then they will not consider those, whether the keywords appear together or not. That information will be lost. So we cannot enforce that type of constraint here.
So is there any version of bag of words that can do text tokens, phrases, as opposed to?
Yeah, you can do it. Let's say there is a way, we call it n-gram, bigram features. So n equal to 2. So you will take 2 contiguous keywords as the features. So I will show you in a minute. So that way you can address that issue some extent. But if your phrase is, let's say, you're looking for, let's say instead of keyword search, you have a question. So in that case, in other words, your query is more than 2 or 3 words. Then in that case, this bigram, trigram will work reasonably. But if it is your query string is 4 gram or 4 words, then the bigram, trigram will not work. That's what I'm saying. There is a limitation also. Okay, now let's talk about the bag of words representation. So let's say our vocabulary collection consists of only these 7 words only. So it's a toy example. So in this case, I'm talking about, so this is my vector representation. Basically, the first feature is he, second word is, or second feature is she, and the third feature is I, and so on. And then I have a sentence or the document. I'm saying I'm feeling good. So I want to represent it as a feature vector. Then in this, using this vocabulary, I will represent he. If it is a binary representation, he is not there, 0. She is not there, 0. 1 is there, 0, something like this. So in a vector representation, it will be something like this. So the first 0, this 0 means he is not there, right, in the sentence. And this one means I is there, right? Then am is there. Then I'm feeling good. Is not there. Feeling is good. Feeling is there. Good is there. So that way I end up with this. Do you understand that, right? So now, instead of I'm feeling good, let's say she is feeling good. So the vector representation will be something like this. He is 0. She will be 1. And then feeling, where is he is coming? He is feeling good. And the rest will be I am will be 0. So something like this. That way we represent. Now you already asked me the phrases. So for phrases we can use this. What we call it? N-gram. N-gram is a contiguous sequence of n items from a given sequence of text or speech. And N-gram, we already talked about the word or token. That's basically n equal to 1, unigram. Now I want to talk about bigram, n equal to 2, trigram, n equal to 3, and quadgram, and so on. So I will show you an example. From there you will understand what I meant. So we have seen a special case of bag of n-grams, bag of words, where n equal to 1. In general, bag of n-grams a text feature technique which describe each document by a vector of n-grams occurrence count. As in case of bag of words, bag of n-gram ignores the location of the words in the document, but it captures the if the 2 words co-occur or not, we can capture it. So now, okay, so my feature representation is this: he, she, I am feeling good, and the bigram representation will be I am feeling good will be what? So I am feeling good. So one bigram will be I am. Another bigram will be I am feeling. Then the third one will be feeling good. So that way, when you generate a feature vector, first you will use the unigram features. All of this I am, each distinct word will be used as features, plus you will use this bigram in your feature vector together. So here I just try to show you, I am feeling, that part is 1, I am feeling, that part is 1, feeling good, that part is 1. So, but ultimately this is not a representation. Ultimate representation will be something like this for us.
What would the vector of the bigram look like?
Yeah, that's a good question.
So,
Okay.
So I am feeling good would be 0, 0, 1.
Okay, so there is a, okay, yeah, let's say my original unigram feature vector is this. I say he, first word is he, second word is she, third word is I, fourth word is am,
It's on the top line of the slide.
Yeah, is, then what is feeling good, right? So that is my unigram features. So that unigram feature vector. So for that I am feeling good, it will be represented. For that I am feeling good document, I am feeling good sentence. The representation will be 0 0 1 1 0 1 1, right? For the unigram representation. Now for bigram we found this. I am feeling good. These are the three feature vectors. Now you will take the another document, you will extract the same way, then you will take the union. So let's say this is the bigram feature FB1, FB2, FB3, and then another document, another sentence I have. Let's say he is feeling good also. So in that case, unigram representation for he is feeling well will be what? 1 0 0, yeah, 0 0, right? Am I correct, or I put too many 0? Yeah. Okay, so yeah, looks like you understand better than me. Okay, so now he is feeling good. For that we will generate like this, and for bigram we will generate he is feeling, then feeling good. So he is will be a new feature vector, bigram features. Is feeling is there or no? No. FB prime feeling good is already there, right? So that will be FB2. So now let's say as a toy example, we have only two examples, two sentences. So the bigram features will be represented by this FB1, FB2, FB3, FB4, and FB. Total how many features we have for these two sentences? Total 5, right? If here 3 and here 2, and the second one feeling good here, right? Overlaps. So now bigram features will have only 5 dimensions. So for this I am feeling good. For that bigram representation will be what? 1 1 1 0 0 0, and then for this he is feeling good. In that case it will be 0 0. Okay, so FB, okay, 0 0. Okay, here it will be 1 0 1 1, right? Do you agree with that? So the first one, we have only FB4, FB5, FB2. So FB1, 2 will be 1, and the rest will be 0. FB1, FB3 will be 0, and that way we will come up with the representation. So basically, given a sentence, you will generate those bigram features and take the union and generate the feature vectors. So that's one way you can do it. So you can see what is the potential problem when you apply bigram, trigram. There is a potential problem. Potential problem is you will find a lot of new by n-gram features, but those n-gram features may not appear in other documents. Only it appears, say, the current document, and that's it. So basically it will be a sparse representation, a lot of zeros. Okay, and then instead of n-gram, there is a generic version called skipgram, which is a generalization of n-grams in which components need not be consecutive in the text under the consideration, but may leave gaps that are skipped over. And n-gram is a consecutive subsequence of length of some sequence token W1, Wn. So in that case, a key skipgram a k-skip n-gram is the length of n subsequences where the components occur at a distance at most k from each other. So that's the definition of the k-skip n-gram. So for example, if I have a text like this, input text is like this, and I want to apply bigram here. So you know the bigram will be what? Researcher hope mapping, mapping how mutated gene, something like this, right? So on the other hand, if I use one skip 2 gram, then what will happen? I will skip, instead of looking for contiguous words, I will skip one of the word. Like say researchers, instead of hope, I will skip that researcher mapping. So there I am getting 1 2 skip gram. So here hope, when skipping mapping, hope how, mapping mutated. So something like this. So that way we will generate additional features. So basically here the goal here is to generate bunch of more features, and we are hoping when we generate more features that may be useful for your classification, for your text analytics area and so on. That's the ultimate goal. And there is no guarantee that it will always work. So you have to play with this, and sometimes certain thing will work, sometimes certain thing may not work. So it depends upon again the data set itself. So now I am trying to motivate you that bag of words is not a good representation. Say let's say we want to trying to extract important features from a set of sports news articles, but do you think player will be a useful features? Probably, it depends upon the data set itself, but there is a possibility that player may be mentioned across all the documents a lot of times. So in that case, it might not be a useful features. If the player is almost repeated in all the documents in your collection, then it does not convey any useful information. And so we want to classify reports into related games, let's say football, basketball, and so on. So not only sports. Under sports, we want to classify them into football, basketball. In that case, player will not be a good indicator. So it might be better to focus on the less frequent words like goal, basketball, something like this. Okay, so now I'm going to introduce you, instead of using bag of word representation with the frequency count or the binary representation, we're trying to use the advanced one called TF-IDF. So we should give you a break, or you want break? So I can start now. So we'll talk about TF-IDF now. So as I told you that for bag of word representation, we will have all the distinct words will serve as features, and then for binary representation for bag of word, we can use whether the keyword is present, then it will be 1. If the keyword is absent in the vector representation, it will be 0. Or we can use the frequency count, but that's not that effective. So for that, what we use instead, turn frequency and inverse document frequency. So each features will have a weight, and the weight will be calculated based on this. Previously, weight was either binary representation 1 or 0, or frequency count, another extreme. But now we are developing third method, which is more effective, using the turn frequency, which is a frequency count, times inverse document frequency. So each features in a document, we want to, in the vector representation, we want to assign some weight, and that weight will be calculated based on this TF times IDF. So TF is basically calculate how many times the word appears in the document or feature appears in the document. That will be the TF, and the IDF will take into consideration other factors. If the word appears very frequently across all the documents, then it doesn't have that much discriminating power. On the other hand, if word is a rare word, it appears only very frequently in a particular document, but it doesn't appear in the rest of the documents. So in that case, it should carry higher weight. That will be captured by the IDF. So IDF decreases the importance of a very frequent terms in the corpus. On the other hand, it increases the importance of a low or rare frequent term in the corpus. So that we try to capture. So that way, IDF will be used to identify the rare terms, and if it is frequent in a particular document, and on the other hand it is rare across all the documents, it doesn't appear very frequently, then it will carry very high weight on the IDF, and it will be multiplied with the how many times the word appears in the document and so on. So that way we will try to capture the TF IDF. So again, let us say each of this document will be represented by 10 vectors or 10 dimensions. So each dimension represents F1 means word 1, F2 means word 2, F2 10 means word 10. So now we are talking about keyword 1, keyword 10, and each of now for this document 1, I am going to come up with a vector representation. So in that case, previously we said if the keyword is present it will be 1, keyword is absent it will be 0, something like this. Now instead we are saying it will be a weight. Weight will be for F1, W1, W2, W10. So for particular weight will be calculated based on the term frequency multiplied by inverse document frequency. So I am saying if the particular term appears in this document very frequent, then term frequency will capture that importance by using term by getting higher numbers here by the term frequency. And at the same time I want this word what we are looking for, that word should appear only in this document or few documents, but rest of the document should not have that word. If that's the case, then inverse document frequency will have a higher weight. On the other hand, if the word appears across many documents, then inverse document frequency will carry lower weight. That's the key point here. So if the word is unique in a particular document, if word doesn't appear in many documents, only appears one document or few documents, then IDF will capture higher weight. On the other hand, if the word is very frequent across all the documents, IDF will capture lower weight. And the term frequency is usually the frequency count within that document, how many times it appears. So that way we calculate the weight. Now here more details. Formally we can say, so term frequency, inverse document frequency for a given word. So the T is the word or the term, and the D is the document we are currently considering, and the C is the corpus. So for that corpus in that particular document D, I want to calculate the weight of the term W. So that weight will be assigned here as a feature values. Is it clear? What is the meaning of this? All this TF IDF. So that will fill up those W. Basically, this W is nothing but the TF IDF. Now, how do we calculate the TF IDF? I'm trying to say consists of two terms, product of two terms, term frequency multiplied by inverse document frequency. How we calculate the term frequency? How many times the term appears in the document D. So we are focusing on one particular document D. That's the frequency count in that document, how many times the word appears. And then the IDF, inverse document frequency, T is the term and the C is the corpus or the collection. So that will be, so IDF I will explain in a minute. So IDF will be calculated, one way is you can do this, but this is not the widely used formula is something else. We use like this, log capital N divided by N. N is the number of documents and small n how many documents contain the keyword or the term T. So if N is N, if N and N, small n are equal, what does it tell you? That means the term T appears across all the documents. Capital N is all the documents I have. And if the term appears across all the documents, the n equal to capital N equal to small n, then this will be log 2 base 1. So 2 to the power 0, 1 log will be 0, right? So it doesn't, so that way we'll take into consideration. But anyway, here we use a little bit different formula, but it doesn't matter. In the most of the literature, you will find this formula they use. But here I just showed you, so C is the corpus collection divided by 1 plus document frequency, the how many times the terms appears in the okay, what is the okay, so the DF is this, the number of documents in C that contains the term T. So that is nothing but this n, small n, right? So and then C is the total collection or the total number of documents we have. So we have n number of capital N divided by, you can say, how many documents contain the term C. So that way you calculate the idea. And now there is a problem with this representation. So it works in the literature, you will find that TF-IDF works reasonably well over the binary representation of bag of words or the frequency count. So for your lab, I think we are going to use TF-IDF. And then, but it introduces some problem also. The problem is it introduces the vector representation. When you do the come up with the vector representation of the feature vectors, many features will be 0. So it will end up with a sparse representation. That's a problem we have. So let's say if I have 100,000 different words as a features, then you will see only this number of features will be used in the report. Then it means 99% cases or 99% features will be 0. So that's one extreme example we give you. Okay, and another problem is, I already told you that this data is a high dimensional. So when you have a high dimensional data points, and if you want to calculate the similarity, you will do the Euclidean distance calculation across those high dimensions. So that will be computationally very expensive, so it will be a problem. And then another problem for these are all bag of words. They call it syntactic features. Say for example, if you say these two sentences, I booked a hotel and I reserve a lodging, basically both represents the same concepts, right? And both should be, if you try to determine the similarity between these two sentences, they should have a very high similar values. But when you end up with the vector representation, either using TF-IDF or along with the, if you do the TF-IDF representation of this, you will end up with a different feature vectors. And if you calculate the cosine similarity or the Euclidean distance between these two vectors, you will see that similarity value is very low. So that means this feature representation, what we are doing here, it doesn't capture the semantic representation. So here the way we represent the feature vectors is more syntactic level. If the keywords matches well, then feature will also match well. But if the two words convey the same semantics or same meanings, then this method will not be able to capture it. So for that, what people use, they use WordNet, map the keywords into the conceptual space, and then do the similarity using the WordNet. That type of thing you can do it, but I'm not going to cover it. I just give you a heads up. And then last but not least, the new method has been evolved very recently, called 5-6 years back, word embedding. So word embedding is a feature learning technique that used to map words or phrases into a vectors. So keep in mind, so far I always talk about document will be represented as a vector, right? Now I'm going to introduce a new concept called word will be represented as a vector, each word. And then from there we will transform so recall that each document will consist of a set of words. And now in the past we showed you that the document document we used to represent document by feature vectors, and in the vector each dimension represents a keyword and so on. Now I am saying in the word embedding case, each word will be represented as a vector, and then later I will show you that from this word vector we can come up with a document vector, that I will talk about later. But now if the two keywords, let us say lodging and I am booking a hotel room, booking and lodging may have the similar meaning. So in that case, if I represent booking as a vector and the lodging as a vector, so in that case these two keywords vector should be similar because they convey the similar concept. So that's the very basic idea. So word embedding is a feature learning technique that used to map words or phrases into vectors. So that's the key important point is this. So each word will be represented as a vector. In the past I showed you that document was represented as a vector. Now in the word embedding case, the word itself will be a vector. So then I will tell you later how the word to vector document conversion we'll talk about later. So there are a bunch of methods for the word embedding. One is word to vec, which was developed at Google. Then there is another method developed at Stanford called Globe, and the third method FastText is developed at Facebook. So we'll talk about one of the model a little bit more detail. So word to vec represents the meaning of the word, and each word will be represented in a lower dimensional vectors. And word similarity means if the two words are relevant or close to each other, then they will have a vector similarity value should be very high. Or if you calculate the Euclidean distance between these two vectors, the Euclidean distance will be very small. The distance and the similarity are inverse, right? If the 2 points are close, that means distance will be 0. If the 2 points are exactly same, then the distance between these 2 points in the Euclidean space will be 0, and the similarity will be the highest, 1.0. So something like this. So the key idea is predict the surrounding words of every word, and from there we will come up with if the two words convey the same meaning, then the feature representation or the vector representation will be the same. Basically they will use similar surrounding words a lot.
So would stemming of a word give similar low dimensional vectors?
No, stemming you just the pre-processing steps we apply the stemming and map the words in convert the word into the root word, that's it. So that way if you do not do the stemming, the problem is connecting. These three words will end up with the three different features, right? That we don't want in our vector representation.
So the similarities between those vectors would be wide as opposed to close?
No, for stemming is different. Stemming is a pre-processing steps. We just convert all these words into their root words, and then those root words will serve as a features in the vector representation. Then after that, I'm talking about we can basically using word embedding, we can try to find the similarity between words. But for that, we will use some pre-trained model, big, large corpus. From there, we try to identify which are the words co-occur together. So based on that, we will do the similarity. I will explain in a minute, and then if you have a further question, you can ask. Okay, so word to vec model is a group of is used to produce word embeddings. These models are shallow and two-layer neural network architecture, so I don't want to talk about that details. But it takes input a large corpus of text and produce a vector space typically of several hundred dimensions. So basically using that large corpus, it will run the model, and each word now will be represented, let's say 300 dimensions. In Google case, each word will be represented by 300 dimensions. So each word will have a vector size will be 300 dimensions. So for example, now with unique word in the corpus, we assign a corresponding vector in the space. What vectors are positioned in the vector space such that words that share similar context in the corpus are located in the proximity of one another in the space. So now let's say sports and basketball and football, they are very, let's say, okay, this is an example. Let's say in the US, the soccer is a sports, right? And in Europe, they call it, what they call it, football, right? So now, when you use the Google fast text, this word embedding, what will happen that just think about the vector representation for soccer, say 300 words, and the vector 300 features. The vector representation for soccer will be 300 features, and each feature will have a bunch of numbers. And then, if you take the football, European football, not American football, say in the context of European documents, the football is mentioned. If you consider those football's vector, so you will see that these two vectors are very similar because they represent the same concept. Okay, so in order to do that, what we try to do here is this. We try to determine this is the center word, and these are the surrounding words. So these surrounding words will represent the context. So the idea here is, if a word represents or used in the same context with another word, then these two words, when they come up with the vector representation, they will be very similar. So this is my center word, and with respect to this, these are my surrounding words. So from this surrounding words with respect to this word, I will end up with a vector representation. So red is the center word, and these are the context word. And from this context word, we will learn from the given training data or the corpus, we will learn the vector representation of this word. So when keep in mind that I said, in case of Google, they use millions of documents to train the model. So they will take each word and find out the surrounding words. And from this surrounding words, they will use those surrounding words will be the context word. Context word, you can define it within the same sentence or within the, if you consider this word is the target word or the center word, from there you will go -3 position, and from there you will go +3 position. That way you define your context or surrounding words, and you train your model and come up with a vector representation for this word. So now what is the application of this? The application is this. When you talk about, let's say, man and woman and king, what will be the possible word here? So here we represent some sort of gender features, right? Gender relation. So it will be queen. So if you do a vector representation, so I said, in this case, each of this word will be represented in a 2-dimensional space or 2 features. So each of the points will be represented by 2 dimensions. So the king will be represented by this, and the queen will be represented by this, and so on. So if you calculate the vector man to woman, the direction will be something like this, king to queen will be something like this. Now the beauty of this, what they show in terms of math, if you subtract this king minus man plus woman, what do you expect? You expect the net will be the queen, right? So if you do the vector representation, this numbers, king is represented by this in a 2-dimensional space, and man will be represented by in 2-dimensional space this 2-dimensional features, and then woman will be represented like this. So if you subtract this, -3 points plus 0.6, 0.9 minus 0.2, right? 0.7. So exactly queen when you learn the queen vector representation, you will have the queen is this value. But if you do this subtraction plus addition, you will end up with exactly same numbers or similar number. So that tells you that this vector representation has some, in the word embedding space, it has some meaning. So they also showed that now they try to determine the relationship between this, let's say Portugal and Lisbon, right? So that whatever relation it represents the country versus capital. So here they try to put, let's say, China.Beijing equal to Portugal and the question mark. So if you do this, Turkey versus what is it? Ankara. Will be equivalent to, say, Italy versus Rome, right? So if this is missing, so we can calculate by doing this type of simple calculation, Turkey plus Ankara minus Italy, you will get some vector numbers, right? So that will be very similar to the Rome. So that way you can, this can be used for various purposes. So basically it represents some relationship. Now how it will be used for our purpose? So the key point here I am trying to convey that word embedding will try to use the word we are considering. For the word embedding, using word embedding, that word can be represented as a vector. Now if the two words co-occur in the same context in the training data frequently, or in a large corpus frequently, then you can assume that in the vector representation, these two vectors, two keywords corresponding vectors will have the similar values. So now we want to use that for our purpose also. So this is the way we are going to use. Okay, the purpose is this. Now recall. So word embedding, what you learn. So what is the benefit of doing the word embedding? It captures the context better, right, as compared to bag of words representation. So now in a word embedding space, word embedding, each word will be represented as a vector. And then now we have a document, right? And each document consists of a bag of words. Consists of a bag of words. So now I want to convert the document into a vector, but this vector will be represented by in a word embedding space. So what I will do? So I will take each word, and now before, when I do a vector representation in the original space, so each document was represented by W1, W2 all the way to 10,000 dimensions, right? 10,000 words I have before I try to tell you. Now I am saying each from using the word embedding or what to vec model. Now you already know from the training that each word will be represented by 300 vectors. 300 dimensions in the vector. So each word will be represented by a vector with the 300 dimensions. Now what I will do? So now I need to convert this document into a vector model in the using the word embeddings, using the word embedding model, or using the word to vec model. So how I can do it? But again, recall that each word in the word embedding model or word to vec, each word was represented by a vector with a 300 dimension. So one thing you can do, so let's say this document has 50 words. So you will take each word, word 1, 50 dimension, word 1 has a 300 dimension, right, from the word to vec. So word 3 has a 300 dimensions. Word 5, these are the word appears, let's say, and all the way to say word number 100 with the 300 dimensions. And you can take simply average of each dimension, and that will be the feature vector for this document. That's one way you can do it. So that we try to do it here. Any question? So that we try to do it here. We will one approach. There are many ways you can do it. One approach is where each document will be represented by weighted average of the feature vectors of the words in that document. So here, how do I do it? So the embedding. So you will take the word, whichever the word appears in the document. Let's say document D. I want to come up with the feature vectors in an embedded space. So for that, because that representation captures the semantic features, or in a better way we can represent the features. So total n number of words in the document we have, and each word we will come up with a what to vec representation, right? So that's a lower dimensional space, 300 dimensions, time the weight of the word. The weight of the word in that document. So turn frequency multiplied by inverse document frequency, the word, time, word and the document, comma, corpus. So this will give you some sort of numeric numbers. So that will multiply with the embedding, the what to vec will give you some feature representation. So that's independent of the document. So this, again, recall that this embedding W means is a feature vector. So this feature vector doesn't depend on the document itself. It is independent of the document. So, but we are focusing on the document D. That's why we are considering the document D's word and then the weight. That way we will come up with this weighted one. So do you have any question for this?
Just find that that's not mentioned.
No, so this is a word we will give, and this what to vec model will give you a feature vectors, lower dimension 300 dimensional space feature vectors. I mean 300 dimensional vector representation. So that but underneath they use what to vec model or word embedding. So there the idea is if they consider all the surrounding words from the training data, they take each sentence, and for a given word they try to identify the surrounding word or the context, and then from there they train a optimization function, pre-train the model and come up with the vector representation. The idea is if the two words are frequently used in the same context or share similar keywords, surrounding words, then in this embedded W for these two words, the feature, let's say what W1 and W2 are considering, those two words will have the similar vector representation. So that's the main idea here. Any other question? Okay, so what is the advantage of doing this? So it avoids, so recall that before we try to represent the document using the 10,000 dimensions, right? Now using this feature D, how many dimensions this D will have? So it will be eventually represented as a vector after this, and these vectors will be how many dimensions? I said this W has only 300 dimensions. So in that case, the feature W will have how many dimensions will have? 300 dimension also, right? Do you agree with that? So I'm saying this embedding what to vec model, I mean what to vec or globe or whatever the model you will use, from the training corpus they will end up with a 300 dimension for each word. Now this 300 dimensions will multiply the weight, and then we'll take the sum and then take the average. So that way this feature D will be represented by a vector with 300 dimensions. But in the so this is the document representation now with the help of word embedding. But in the past, if I don't use the word embedding, if I only use the simple bag of words representation, I said we will end up with the 10,000 dimensions. So here you can see the dimensionality drops. So word embedding doesn't suffer from the sparsity problem and also the dimensionality issue in the higher dimension. And it tried to capture some sort of context. That's the main advantage. And when you try word embedding, what I noticed that the result improves 2-3%, not that much. If you use a bag of words instead of what to vec, let's say bag of word gives you 70%, and then when you use word embedding on top of it, it may give you 70 to 73% on average. It's not very significant, but it's still good. And it gives you faster processing, those type of things. So I'm almost done. I'm sorry, too much time. So here I try to tell you that text pre-processing steps, including the removing the stop words, do the stemming, and we try to talk about the tagging, name entity, and bag of n-grams features. Then I talk about the TF-IDF, then I talk about a little bit word embedding, and that's it. So we will start the homework hands-on one. Do you have any question for me?